For the next 2 hours, we're going to talk about VXLAN EVPN. I try to give you a deep dive in some areas of how the control plane works, how the data plane works, and so on and so forth. We are related to data centers, so we look at NXOS related function, and I'm going to try to guide you through this. My name is Lucas Kradiger. I'm a principal engineer working out of the data center business unit. We do everything Nexus and ACI related. For the next 2 hours, it's all NXOS on Nexus, which we're going to discuss. Short journey on what we're trying to do, short overview of our overlays to not make you all wet right at the very first minutes. Standards and implementation on VXLAN, BGP, EVPN. So I will talk a bit what the standards bodies are doing, IETF, what kind of versions we are having there, a little bit about that. Walk through about control and data plane, and at that point we're already pretty in the deeps, trying to show you what happens in the control, what happens in the data plane, how these things come together, and then a couple of packet walks. You guys are good with that? Yes? Okay, very good. A network, an overlay network is only as good as the underlay, because that's my transport where it goes on top of. So I need a switch and I need a couple of protocols, a couple of IP address, a routing protocol there. So we'll also talk about some of these considerations in that regards as we're going through this. I have two more sections there, two more evolutionary sections. One is what we call TRM, tenant routed multicast, so how we do multicast routing in a VXLAN overlay with EVPN. As you might remember, VXLAN is a layer 2 encapsulation, so there's no routing at all. So just BGP EVPN make it route, right? And then there are some address families there, right? EVPN is an address family on multi-protocol BGP, so we need another address family for doing multicast, which is MVPN or NGMVPN, which we're going to look at how this really works and the difference on the standards implementation, which is there today. This is the agenda. So basically everything I said we're going through. I added two pieces which I thought was missing from the previous one. One is around distributed Anycast gateway. I think I kicked that out last year and just said, I'm talking about integrated route and bridge that should suffice. I don't think it does, so we'll talk about this one. And then also the VPC implementation together with VXLAN EVPN, which gives your host kind of a redundancy. And I think we have all single attached hosts, but dual attached hosts is definitely something we need to take care on to create that resilience in my data center. Last point is a segue. I used that as a segue for another session we have. It's around DCI, Data Center Interconnect. We call it multi-site in VXLAN EVPN. We call it multi-site in ACI. So the concept, the direction is the same. Implementation is slightly different. So we're talking here about just the conceptual part on what we're doing on the VXLAN EVPN side with NXOS. And then there's a whole session tomorrow morning at, I think it's 8:30, which Max Ardica and I'm going to do, and just talking about that one topic, multi-site. So join us there if you are interested. So with this, let's dive right away into, and I want to give you a little introduction into overlays, the components, some of the terminology, and some of the concepts which are happening there, some of the puzzle pieces which are there. So in the essence, as I said, the starting point is what we call the underlay, the transport network, right? How do I communicate from one switch to the other one, right, in this whole scenario? And there are topology discussions. Most of the topologies today are class topologies or leaf spine as we know them. And the transport which we're using in VXLAN, which is an IP encapsulation, is IP. So we're building that underlay with IP. Important in these areas, from a taxonomy perspective, is the edge device. The edge device is the device which sits between my host or my router and my VXLAN network or my fabric, my overlay, which I'm going to introduce. So that's kind of the most important piece there, and very often you see that positioning of that edge device at the leaf, right? So that's where he normally belongs. So the whole intelligence in such a leaf spine topology, in such an overlay fabric, goes into what we call the edge device. That's where certain of these functions are hosted. Southbound of the edge device, we have a LAN segment, a local area network, an Ethernet in most of the cases, and this could be for virtual as well as physical server. Is it an access port? Is it .1Q trunk? You choose. right? There are even certain consideration on where you're having stitching of different kind of encapsulation at that edge device point, but this is the predominant approach you're doing in a network overlay, as what we're going to talk today. Between the leaf or the edge device and our spine up there in the middle, the spine is my backbone of my network. That's where my bandwidth and my resiliency comes in. There I built that IP network, and what I tend to say is the first command I enter on these interfaces is no switch port, which basically makes that port an IP interface. So there's no VLAN tagging, there's no trunking on these red lines. This is nothing else than one IP on one side, another IP on the other side, and then a handshake of a routing protocol in between. Make sense? So far, so good? Am I too slow? I can go faster. Try not. When we clap an overlay on the top, I said we have an underlay, right? And then we clap something on the top, which is an overlay. We need somebody who is the originator of these tunnels, right? Of that overlay tunnel, and that's what the function of a VTEP is. VTEP specifically is the VXLAN tunnel endpoint. We very often talk only about TEPs, tunnel endpoints, just in generally. And I guess all of you saw many TEPs over your course in the industry. GRE has a TEP. It's called Interface Tunnel. IPsec has actually also a TEP, but you're not actively configure it, right? But all of these tunnel, all of these overlays concept have a TEP, and the TEP is hosted on top of the edge device. So edge device is the switch, the TEP is a function on the top, the TEP is represented by an interface. In our case, on our implementations, the interface NVE1, and then redirected over a loopback where that is reachable. Now, from this tunnel endpoint, you have a tunnel encapsulation which runs between all the tunnel endpoints. I said before, I was talking about GRE, right? GRE was mostly point-to-point when we started with, and then became some point-to-multi-point subsequently. VXLAN is a multi-point tunnel. It's a layer 2 multi-point tunnel, and that's what we're using as the tunnel encapsulation in this session today. And a tunnel encapsulation, a new kind of network you're building there, needs a namespace. So you need to address a segment in a certain way. And as VXLAN is a layer 2 encapsulation, the namespace there is called the VNI space, or the VNID space, which is the VXLAN network identifier, which is traditionally mapped from a VLAN to a VNI. And you configure this actually on the edge device and associate it to the VTEP. So now you see how this story slightly comes together. Make sense? Everyone fine? Next piece is the puzzle here. There are 5 distinct components in an overlay network. And they are at different areas of the functional component of an edge device or of the network itself. There is, for example, the service. When we are talking about service in an overlay, we're talking about layer 2, bridging, or layer 3 routing, or hybrid layer 2 and layer 3. So that's where your endpoints are sitting, where your hosts are in, if they can talk to each other in L2 or L3, that's where the service is. Very, very often, we're talking about services, and then everyone thinks, oh, L4 to L7. That is fine. But every L4 to L7 service uses L2, L3 transport service in the fabric in order to communicate between the different switches or edge devices which are there. So here, purely L2, L3 in there. Tunnel encapsulation, I mentioned that. So when we create an overlay, we have to somehow slap a header on top of it, because otherwise we see the naked truth of what my host sends. And I want to abstract that. So that's where the tunnel encapsulation in there, and that abstraction happens on top of the underlay transport network on the top right there. 2 additional things which are important for such overlay technologies is the control plane and the data plane. So the data plane is where that slapping the header happens. The chip who knows how to take something addition on an existing Ethernet frame or IP packet which is coming from the host. That's a data plane operation, how we call that. And in that data plane operation, there are 2 things happening. One is just forwarding unicast. That's easy, because unicast goes exactly to somebody, right? It goes to you. It will not go to you. It's a unicast, right? But when it goes into broadcast or bump traffic, broadcast on unicast or multicast, it's multi-destination traffic. So it's a replication approach to multiples. That's also a data plane function, right? And in VXLAN, there are 2 ways on how I can do multi-destination traffic replication or BOM replication in short. One is what's called ingress replication. That would be like me going to each of you individually and explain this whole 2-hour session. Or there's multicast, where I can take a microphone and you all hear the same what I'm saying at the same time. Does it make sense for everyone? So when you hear about VXLAN EVPN doesn't use multicast, it's actually not entirely true. Multicast can still be part of it if you use efficient replication. It's also true that VXLAN EVPN assists ingress replication in a more dynamic way. By all of you telling me who is interested in actually what I'm saying up here, I can officially go to you individually and talk to you about this. But you first have to tell me interest. And that's what's happened in the control plane. And that's why many people say BGP EVPN uses always ingress replication, which is actually not really the case. It's an assisted replication which we're doing there. Which leads us a little bit to the control plane. It is about peer discovery. How did we do peer discovery in GRE? My IP, your IP, that's the tunnel. In a full mesh in a data center across multiple of switches, this is becoming very hard. We call that pseudo-wire maintenance or tunnel maintenance, where you have to build all this. We don't want to do this, so a control plane can help. The cheapest control plane on this earth is called flood and learn. You send something in, it goes everywhere, and by accident we learn where something happens. A more intelligent control plane, what we're using here is BGP or BGP EVPN, a very specialized address family. So I create a peering, and I learn about all of you guys, because you're a TEP to me, you're part of my domain, and that's where what the peer discovery comes in. Because I don't learn about you, I cannot send you anything, or you cannot send anything to me, as we don't know of each other. On top of the peer discovery, there's an additional piece which is called the local and the remote learning. The local learning means I'm a host, I'm connected to an edge device, so that edge device learns a MAC address or an IP address when I ARP or do ND. This information is local learned on that switch. And now I have to tell all my peers about that, and that's where the remote learning happens by me using the BGP EVPN control plane to sending a BGP update to all of you, that you know that behind me as a switch, there is a host connected with that MAC address, with that IP address. And that's exactly what the most of the part is of today's discussion for the next couple of minutes we have left. Click. I made jokes about the clicker, so I have to be careful that I also push the right button. So when we go into the standards and the implementation of EVPN, there are two parts we have to look at. One is definitely the control plane work which is happening and how the control plane is specified for the respective data plane. So we have a data plane which we want to talk about is VXLAN. It's completely separate RFC, it's 7348, it's a UDP encapsulation, it uses layer 3 transport, all the good thing we already discussed. So that's one piece. We leave that on one side separate. On the other side, we have a control plane which is EVPN. Sorry about that. I clicked once too much. Which is, again, a separate RFC. And very, very recently, the RFC 7432, who specified EVPN for MPLS, it's still there, stays there, it's for MPLS specific. We moved into the RFC 8365, which is EVPN for NV overlays, or IP overlays, or VXLAN in that case. So when you look at some of the standards-related work which is happening, you really have to be careful on what kind of control plane you're actually looking at, because there are 3 distinct variations for EVPN depending on the data plane, which is MPLS, provider backbone switching or bridging, or overlays VXLAN as in NVO3. And this is what we're going to talk about that. You guys are all champs on this one, right? You all knew about this. Yes? Everyone fine? This is the list. If you get insomnia, that's the one you like to go through. I tried once, I tried twice. It didn't help me to sleep here, so I'm still slightly jet-lagged. Apologize for that. But whenever we do all of this RFC digging or looking at these details on control and data plane implementation, on the top of the pyramid is always a use case. I want to do something. Why am I even going to look at EVPN? I want to, or VXLAN as an overlay. I want to do something, right? There's some need I have. And at that point in time, I have to think about what I want to do. And we had exactly that that thoughts when we started doing VXLAN EVPN, what do we want to achieve? So the network deployments, the industry is moving to something what we call host-based routing. So doing as much as routing as possible, because that large layer 2 stuff is sometimes biting me somewhere. So we try to combine certain things. And we looked at this whole story around EVPN, and we figured there are actually two very distinct use case strains. One is focused on a layer 2 service, which is very, very often used in Metro, Ethernet, in the service provider world, and so on and so forth. And the other side, there's an integrated layer 2, layer 3 approach. So all about optimized forwarding, all about reduction of unknown unicast flooding, and such, like a great job for using this in a leaf-to-leaf communication horizontally in the data center, east-west, where probably every connection coming from the outside into the data center will be multiplied by 8 to east-west communication within the data center. At least that's what we saw approximately 6 or 8 years ago when we made all of these research around that. The reason why I'm saying this, in EVPN, there are use case-specific implementation options. I'll call it options. Recommendations is wrong because nobody tells you what you have to implement from a standard to a vendor, but there are different options in there. And there is one side which focuses more of having a layer 2 network and giving you the option of doing a layer 3 instance at a point. Or there is an option which always considers the layer 3 part as the first thing to solve by adding a layer 2 connectivity in addition to it, right? So when you think of that, how many applications today still require layer 2? Some. Do we want to get rid of that layer 2? Yes. Have we tried with all the great stuff with IP fabrics and these MSDC approach? Yes. And there is somewhere very, very back in the rack the application everyone forgot about who has a heartbeat in layer 2. And all my designs and stuff falls apart and I have to go back and build some cables or move the servers around or something like this, readdress servers I don't want to. So we wanted to give that option. So in EVPN, when we look at the L2, L3 approach, there's something called symmetric IRB. I'm going to explain what it is. It's integrated route and bridging in a symmetric fashion. There is another piece which is called VLAN-based. So we are a VLAN-based approach of creating, let's call them layer 2 VPNs to start with. And then there is a VRF to VRF routing option. And as you can see on the other side, where layer 2 only is considered, there's no VRF, no IP multi-tenancy. I cannot create IP VRFs. I can just create the layer 2, and I can give you a little bit of first-hop gateway. And that's why we decided at that point, when we made all of this, we decided to go to the layer 2, layer 3 implementation approach, and that brings us, as a first topic, to what is symmetric IRB. As I said before, it's a routing-first approach. So I bridge from my host to the first switch, to my first hop. My default gateway sits on that first switch. So I'm not going layer 2 all the way through the whole network to find somewhere somebody who might be my first hop instance and use HSRP, VRP, or you name it on top of that. I'm going right away to the first guy, and he can do a routing decision if I want to route. So we evaluate at that point, bridge or route. If we do route, we route into what we call IPVRFs, transport it to the network, and decapsulate and bridge down to the exiting host. And that's what symmetric IRB does. And it's called symmetric because in both directions, we use bridge, route, route, bridge, route, route, bridge, and we are in the same VRF and the same IPVPN. I'm going to show you a couple of diagrams for that. The other piece is what is called asymmetric IRB, or inter-subnet forwarding. And it's asymmetric because it always does a bridge and then a route only on the ingress side. So only where the packet hits the first switch, I route there. And I made my route decision, and then I bridge through the whole rest of the network to reach my server on the outside. Why is this asymmetric? Because when I route on ingress, my path from host to the remote subnet will be different than from my destination host to my subnet, because it's different subnets. So let me clarify that. This is how symmetric IRB looks like. I have bridge to the MAC. You see the IP there. I'm blue. I'm going into that VNI, which is our layer 3 IPVRF instance, our route between the two. I decap and I bridge down to the host. So bridge, route, route, bridge. As a result of this, my ARP tables are local. I don't need to learn about host B on the first switch, because I don't care. I route to that guy. ARP is only necessary on the first hop, right? You all agree? So think of this. I have now, today, an Ethernet network, and I have to store all my ARP table of my whole Ethernet network centralized. Wasn't that a pain point at a point? Wasn't it? You guys never had that issue? ARP table too small? Don't have that problem anymore because now we distribute it. The same thing happens actually from a routing perspective. So we do now host routing. That brings it down, right? The cheapest part in a switch ASIC is what we call a hashing table. And a hashing table doesn't have a prefix. So we don't have a subnet mask, if you want so. And we can store thousands of entries in there. It's very, very cheap because we don't have to look at what length is that prefix, right? It's just there. And we have current entries are going up to 450,000. So I think that should work. That's probably ARP tables were, MAC tables were somewhere at 16K, 64K, and then kind of became difficult. Here we have way larger tables which we can deal with. But you also see that we always follow the routing table when we go from one subnet to the other subnet into the VRF. And that means when you want to go and sniff traffic between hosts in two different subnet in a given IPVRF, you just have to go and filter based on what is my VXLAN network identifier, which is being used for that IPVRF. That's basically the essence there. How you figure out who is where and how does such an update look like? This is how the EVPN control plane entry look, the BGP update looks. You see there, I have a host in there. You see a MAC 48, you see a MAC address, you see an IP address, and based on that, we are populating the local switch information. So you have local learning, and then you have the advertisement and the remote learning. And there's a question back there. I hope I can hear you. Okay, very good question. So are we going to introduce an additional subnet in order to do that blue routing piece? And the answer is no. We're using an unnumbered approach. I'm going to talk about that a little bit later in the section on how the IPVRF to IPVRF communication is happening. Very good question. Thank you very much. If you want to go and read, section 3.2 of the EVPN inter-subnet forwarding draft basically specifies exactly what I just told. We're using an ingress-egress kind of routing approach, bridge route, route bridge. Now in asymmetric, it looks different, and that's where I want to come to the asymmetric part. You see this flow here? This is host 33 wants to talk to host 44. They're in two different subnets, right? So when I come from 33 and want to go to 44, I do routing on ingress. That means I do the routing exactly here. And that means at the point where I'm post IP, I'm already bridging to the destination on where my host, 44 is. So I bridge into green. So it's actually a MAC rewrite on ingress, if you want to be correct. But we call it routing. How will the reverse look like? I said I always route on ingress, so my reverse also has to route on this body here. That means I have to create orange there as well. So if I want to route between two subnets in asymmetric IRB, I have to have every VLAN, every subnet configured on all the switches or have a centralized gateway. Subsequently, that means my routing table, my ARP table will be again how? Everywhere the same. So I'm going back to where I was with a pure centralized Ethernet SVI HSRP approach with a little of an advantage of doing routing on the edge. But as said, we decided to symmetric IRB. That's why it was the slide before green. Everything what you see in our implementation is symmetric IRB based. Everyone fine with that? Nobody asking for asymmetric IRB? Not yet. I guess you come after this session then and ask me. One asymmetric IRB or one question? Is it possible to include something like PBR? You always can do source-based routing with PBR, right? The possibility exists. And actually in symmetric IRB, we have PBR support to oversteer the existing routing table if you wish to do that. Asymmetric IRB doesn't really have a routing table in the traditional sense. It's more of a routing rewrite or MAC to MAC or ARP to ARP kind of rewrite. So there, yes, you could do a PBR, but the question is to what are you routing as per the initial definitions. Asymmetric IRB doesn't have a VRF, and that's why you're not seeing IPVRF to IPVRF forwarding here, because it's a pure ingress approach. You need a symmetric IRB approach to do routing in its essence from a conceptual approach. All right, long talk, next piece. There are 2 layer 2 service interfaces. There are actually 4. I go down to 2 as these are the most dominantly being discussed. And one is called VLAN-based. It basically means that every VLAN has its own EVI. EVI is the EVPN virtual instance, or your layer 2 VPN, or your MAC VRF. You guys are all aware of what an IPVRF is, right? IP, VRF, VRF context, and so on. So it's a virtualized routing table. So what you're doing here is a virtualized control plane table for MAC addresses. So we suddenly have a route target, a route distinguisher on a per EVI or MAC VRF if you want so. That means we do here have that route distinguisher and route target. We do a one-on-one mapping for such a single subnet per EVI between what this instance is and how the transport to the rest of the world, the VNI, the VLAN, etc. is. There is another approach, which is actually kind of a bundle service approach, which is called VLAN-aware. And VLAN-aware does something very different because it bundles all these MAC information you're having for a given EVI together, and you have one route target. So why is this bad? It's not that bad. It can simplify your configuration piece. But on the other side, you have one route target to decide what you take from the control plane and install on your switch, right? So let's make an example. I have 90,000 MAC addresses in my control plane, and all of them are in 1,000 VLANs, and all of them have the same route target. I have a switch which has one VLAN out of these 1,000 VLANs instantiated, and that a single VLAN is in a MAC VRF, which uses the route target for all these 90,000 MACs. So what happens? Based on multi-protocol BGP, route target import policy, I'm going to download all these 90,000 MAC addresses. Great, right? So it's a granularity discussion. Let me go a little bit deeper into the details here. VLAN-based, you see one VLAN ID, one EVI, one route target. So I have very, very granularity on a VLAN-based to what I want to import, which allows me to say, on this switch, I have this VLAN, on that switch, I have that VLAN, and the MAC addresses of each other will not be installed if I don't configure that. So I have that granular BGP policy, which I also use in IPVRFs like for years, right? By the way, that's where it's written if you like to read. And this is how it looks like. I just pointed out one little orange up there in the control plane update because that single 0 up there must be 0. And now the discussion somewhere comes, why can one option and the other option not work together? Because certain things are very explicitly defined in one option, differently defined in the other option. They address different use cases. They will not interop together, even if it's part of the same RFC. So that's an option decision tree you have to make us as an implementer on where you want to go. Here again, that's basically what it defines. So that was VLAN base. You want to see how VLAN-aware looks like? It looks like this. I just did 3 VLANs, 3 VLAN IDs. It's in one MAC VRF. It's a bundle service. I have one route target. So everything which belongs to this EVI will be downloaded on the switch once configured. So you want to have every VLAN everywhere? Yes? Every MAC address everywhere? Every ARP entry everywhere? That's when you go layer 2. We try to optimize, we try to save table spaces for you as much as you can, even as we have in the meantime ASICs which have table spaces at factor of 10 of what it was at the point where we made the decision. But the granularity, the operational option to implement policy is pretty critical. VRF to VRF communication. VRF Lite is great, no doubts, but it's a lot of routing peerings. It's a lot of IP addressing I have to configure between these switches. Now again, going back to a horizontal leaf layer where you maybe have 200 of them. Think of how many sub-interfaces you have to create in order to create these point-to-point links for that VRF flight approach, or you go back and do a trunk, a VLAN, and then you have again a spanned layer 2 domain there. So I try to not do that. In EVPN, there is an IPVRF to IPVRF model in there. It's how we do routing. It's a slightly different route type which we're using. It's called the route type 5, which is an IP prefix route. And in that respective draft, which is talking about this IP prefix routing, there is also a model, or there are actually 3 models defined on how one switch in a VRF talks to the other switch in a VRF. And as the gentleman previously asked, do I need now an IP address on all of these different, we call them fabric-facing interface? And I said, no, we use an IP unnumbered approach. In very correct term, we're using an interface-less approach. So for us, as a VTAP, as an edge device, being part of a VRF, I don't have an IP address in that VRF. I don't even have an interface in that VRF. We're letting VXLAN deal with this. And that's exactly where the convergence of EVPN and VXLAN comes together. There's a tunnel association in the back, but in fact, it's a purely interface-less approach. There are 2 other models. They're called interface full. It's with 1 L because it comes from beautiful. It uses a route type 5, but now, as I said before, I can do that with trunks, right? And then when I have trunks, I need MAC reachability information because I need to do somehow a MAC distribution. In layer 2, I need MAC first, right? And then I need an IP address, I need an ARP entry respectively, and that's where actually in these other 2 models comes an additional route. So for every prefix you advertise, for every subnet you advertise, you have actually a next hop route which comes in addition, which is a couple of more routes which you will have in your control plane. There are a couple of interesting use cases around that which make sense to have these modes. We decided to go the simple way, that you don't have to create interfaces or additional route or overhead. Like I said, the optimized way. That's where we decided on interface-less. So when you go through these slides subsequent, the green part is what we implemented in NXOS or in Cisco generally. So you can follow kind of that part, reread, and ask me questions if you want to. Investigative questions, I always like them, and sometimes I'm even able to answer, so because sometimes I don't know. This is interface-less. It's a single route. Similarly, as you would think of an OSPF route or a BGP route, it's a single route. It has every information in there you need in order to route from one subnet to another subnet, or having multiple VRF instances there to have that differentiation going in there. You see down there, I have some NCAP there, I have some types there, and I have a router MAC there. As I mentioned, when I do routing, I somewhere need a MAC or an ARP entry or whatever it is. Here it's purely in the route type 5 identified and mapped against the next hop address, which is my VTAP IP address, a loopback on another switch or router. If you like to, this is the section you can read about this. Now, I shortcutted a lot on the blue section because we could probably spend another 2 hours just on blue versus green or the details on blue and green, but I want to give you a little bit more on what we're doing in the green section or what we're doing in Cisco in NXOS specifically for our implementation. And we're already 30% of slide through, so we should be good in timing, and I should not need to rush. How is a host advertisement working in EVPN? It's working that we have a host connected to a switch. That's the baseline which we need to have. And if that host is there, what does it do normally? Broadcast, sends out some frames, or get recognized by the switch. And when it gets recognized by the switch, what we're doing is we're creating a control plane entry, and we're creating a control plane update. So this could be an entry you would see in a route reflector. This is a so-called route type 2. And you see it's MAC only, because that host might not have an IP address today. We have to make sure that layer 2 only, MAC only, does work. And we know it's in a certain instance, in that case in a MAC VRF, in an EVI, represented by the L2 VNI. That's how we would communicate when we encapsulate. It has a route target attached, and it has a next hop. And the next hop is where we would send traffic for that MAC address when we somewhere have an order to forward a packet in this direction. We would do this for the next host, just to give you a little bit an example on how that looks like. And I, on purpose, enter 2 hosts in the same subnet and a host in a different subnet to show you what is actually changing when you look at the MAC-only route. And you can see that in that L2 VNI and RT part, there is a change in there, right? We're using a different VNI for bridging in one VLAN or the other VLAN. It's just now a VNI. Sorry for the shortcut of using VLAN. And each of these VNIs, these VLANs, are in that MAC VRF construct, and they have separate MAC VRF constructs. So we have that multi-tenancy on layer 2 being present there. So this is a MAC only. The type 2 in EVPN has mandatory a MAC entry. So it always has a MAC entry, but it might not have an IP entry. IP is optional in that case. It always has a label. It comes as the first RFC on EVPN was 7432, which was MPLS-based. And there everyone was talking about label to identify the VPN space. So this here is my VPN label for the layer 2 VPN service, or in VXLAN terminology, the layer 2 VNI, and then the respective route target for the MAC VRF. And as I said, this is mandatory. This is how it looks when you really want to do a show BGP output. There are probably 10 better commands to get all these information, and these 10 better commands will tell you what is really on the switch, because this is just a query from a route reflector or what is in the control plane, which we sometimes call kitchen sink, because there's everything in there, right? So everything hovers in that EVPN. You see the different types, the fields, the MAC address length, the MAC address. You see there's no IP. You see what the next hop is. So you can kind of navigate through this by this slide here for your reference. Now, how do we get an IP address from a host? What are the 2 options we have? Anyone? We have ARP. What's the other one? Anyone? No IPv6 guy here? It's called ND. I cannot send an IPv6 ARP because it's called ND. I'm always falling in that trap. So we're supporting v6 and v4 seamlessly in there. So in that case, the host would come online. The host will have his NIC coming online. And normally that's when hosts start ARPing, right? Generally. So we will use these ARP information as they're being locally learned on that switch where he is connected. And at that point, we are actually gleaning this information and populating the control plane. We're not just taking the info from the host, entering it on the local switch. We're also populating this information into the control plane, i.e. BGP, EVPN here. And now you see there's suddenly an IP part in there. So you see an IP part, and you see an IP length, which is a /32, so it's a host route. The route type 2 will only have a host route. If you see something else, might be strange, could be, but you should only see /32 or a 128. Sorry for being pathetic here, not pedantic. So you get also, as a part of being in an IP context, you also get your IPVRF context information. So now you have a layer 3 VPN info. And you see that the layer 3 VPN infos are different than the layer 2 VPN infos. So we send it differently depending on if you route or if you bridge. And we're also using different route targets. Have you ever tried to import an IP address in a MAC address table? I tried, it doesn't work. Have you ever tried to import a MAC address in an IP control plane? We tried. It was called OTV, and we used ISIs with a specific TLV. But to move that inside, you need specific tables where you import the respective right formatted information, and that's why we have 2 different VRF contexts, a layer 2 VRF and a layer 3 VRF for the respective information gathering and information distribution. So you see here host B, and you see here host C. Now, subsequent on looking at this control plane back here behind me, what would you say? Can host A, host B, and host C communicate? The answer is yes. Why? It's the same layer 3 VNI, right? It's the same IPVRF where they're participating in. So I can do now seamless routing or bridging between whatever host, between these 3 hosts, however I want to. How do I determine if I bridge or if I route? If my destination MAC address is a host MAC address, I bridge, because it's not the switch itself. If my destination MAC, where actually my frame is going to, or respectively my packet, is the MAC address of the first hop switch, which we call the default gateway MAC, Anycast gateway MAC, or AGM, then we are forced to do routing because that's myself. When it's myself, I have to route. When it's somebody else, I just bridge it through. It's MAC IP. It's again a type 2. We have way more information now in there. As I said, all the IP attributes are optional, and it's populated to ARP and neighbor discovery, depending on if you're v4 or v6. How does the output look like when we do the same query in BGP? It just has some more information, right? Where the quad zeros were for IP address is now an IP. Where the 0 was for the length of the IP, you have now a 32. Where you didn't have a second label, the MPLS label 2, you have now the layer 3 VPN instance. And then there are a couple of other attributes coming in. For example, the route target, which is in addition for the layer 2 VPN as well as for the layer 3 VPN in there. What else can we do? We can do subnet route advertisements, so IP prefixes, something else than /32 or 128s. How are we doing this? This is magic, guys. Now, wait. We glean based on the ARP from the other router what subnets are behind, and then we magically bring it in. No, joke aside. What we're doing is we're doing a routing peering. BGP, ISIS, OSPF, in the respective VRF where you want to have that route. So it's a control plane peering. Whatever comes over that control plane, we consider being an external route. So we take this external route and make them an IP route, an IP prefix route in EVPN, which is called a route type 5. And do we need a MAC address for that? No. So we strip the format, remove the MAC part. There is only an L3 VPN instance in that case, L3 VNI, the only label we have there. It's only the IPVRF route target we're using there. And we're taking that route coming from the outside and putting it into the EVPN table. Super magic, guys. It's amazing how that works. This is how it would look like when you do the BGP query. It looks pretty much the same, but it's shorter in length and has less attributes in there. One thing I didn't tell you, there is a command we have in our switches which is called, I think back at the times it was called redistribute connected. Today it's called redistribute direct. So when you do this, it becomes a route type 5. Because what have we done? We took it from a local routing table in my switch and put it with a redistribution into the EVPN control plane. So it's considered an external route. So there are two ways how you can bring information in. It's you learn locally, if you want to call it data plane. It's MAC, bridging, it's ARP, it's ND. That's one. Will always be a route type 2. If you use a control plane to learn, it's always a route type 5. Two different things. Can a /32 be a route type 5? Yes. If I do a loopback, say redistribute direct, becomes a route type 5. If that route type 5 has exactly the same IP and length as a host you learn, who will win? Anyone? The host? MAC always wins. Why? EVPN, the E in the beginning is Ethernet. So the local attachment, that's where the first use case is in. So local wins over redistribution or external learning. All right. That was a little bit of EVPN and how we learn certain things and how we do it. And there's that other component. It's called VXLAN. It has nothing to do with control plane, right? We talked all control plane right now. This is the data plane. And the data plane is an encapsulation. So we take an Ethernet frame, slap a header on top of it, and we call it VXLAN. That header has a couple of information in there. Most importantly is what we add to an Ethernet frame which already existed is IP and UDP. The reason why we do not only IP is the learnings from GRE. When you do a GRE tunnel, source and destination is always the same because there is no port which is there, right? It's an IP protocol. When you add UDP, you can play with the ports. And what does it help when I play with the ports is I can avoid polarization. Anyone did OTV? Some of you, yeah? You remember what the NCAP was? The most outer header was GRE. That had the problem of polarization. So you have like a full mesh n times 10 gig, and you only use one because it's polarized on that single link. We fixed that with a couple of approaches. But when you go and look at very, very early drafts of VXLAN, or even implementation of VXLAN, you will find one very interesting thing. The UDP destination port was the OTV destination port. So a lot of the things which were learned during GRE, OTV, and all of these things all flow into VXLAN. And actually, the original OTV encapsulation, which was written down in a draft, was almost equivalent to what the VXLAN was. The only problem was at that point in time, we didn't have a chip which could do it. But GRE was there. A little bit of history, sorry about that. But as said, source and destination IP, MAC can change hop by hop. We don't care on that red outer MAC there. It just has to be modified. Important is the outer IP header and the outer UDP header, specifically the destination, which tells me that it's VXLAN 4789. And more importantly, the source port, which changes. The source port is changing based on the original frame, the 5 tuples. So if we communicate together as an original Ethernet communication, or V, these are different 5 tuples because you have a different MAC address. You are different than you. So that will change the UDP source port in VXLAN. And that means when I route that over a DCMP network, equal class multipath network, the hashing will be different. That means I use a different path. And that's how I avoid polarization. It's called entropy. Some more info on the frame format. It's a MAC and IP encapsulation, and we can go through all of them. Important is VNI. Important is IP. Important is the source port and the destination port behavior. And then you're pretty much good. You guys agree? You're fine with that? Or I want to go through all of them? Okay, not yet. When we put things together, right, we have the control plane, we have the data plane. You see on top the control plane, you see on bottom the data plane. And now I want to send out, in that case, it's probably bridging. I want to send out information. I want to communicate with someone, and I figured out with who I want to communicate. It's with that MAC address you see here in the control plane there. So I need to take these information from the control plane and populate it into the data plane to do the right encapsulation to whoever I want to talk to, right? So I need to take this information, and the first thing what I need is, where is that host actually sitting? Where is that MAC address? And that's the destination IP address. So I populate the destination IP address from the control plane, which is my next hop IP address, and use that for the outer header population. The other thing I need to know is in what context are we talking? Here it's a layer 2 VPN context. We see that in the control plane. We also have a layer 3, but we want to bridge, as it says on the bottom. So we only use the bridging context. This is the layer 2 VPN context there. And also the MAC address, which we actually preserve from the original frame because that's where we want to talk to. So this is how you put the things together. I'll give you a little bit more, as this looks very abstract. I'll give you a little bit of a packet walk on how this would work. It's the same control plane information on the top right. And you see host A and host B, and we want to talk between host A and host B. So the first thing is host A has to generate a packet going to host B, right? And that first packet or frame hits my local LAN segment and it hits the top of rack switch or the edge device in that case, which says, okay, I want to go from A to B. And we are in VLAN, I think it's 101. Tell me, control plane, how do I get there? Well, control plane was smart, already downloaded everything in the hardware table before. It said, hey, I have a hardware entry. I know that this MAC address sits behind Tor number 3, and that's the next hop IP address, so let's encapsulate. So I'll take this information, create the VXLAN encapsulation, and send that over my leaf-spine network. And now you see what has been added is SIP and DIP, source IP and destination IP. So from Tor 1 to Tor 3, I added the VNI, which actually should be 3001 and not 30,001 in this case, which tells me in which VNI space or in which VPN space I should be. And then I kept all the original information, excluding the .1q header, because VXLAN doesn't preserve .1q headers. We are mapping that to the outer. So this is how basically forwarding works in bridging from a host to a host, EVPN, VXLAN combined. Everyone okay? Now let's do it a little more difficult. Let's do routing. Because now with routing, we have a little bit more attributes. We have MAC, we have IP, when is MAC, when is IP, and we have a VRF instance. So regardless of that, in the control plane for routing, when we want to do routing, we want to use the IP information, so we want to go to a destination IP in that case. Now, there's one more information I require. And I mentioned it on many, many slides before, and I never talked about it. It's the so-called router MAC. You remember when I said we need somehow that interface-less routing space for this multi-tenancy VPN approach there? So somehow I have to identify all of these different nodes and actually identify them by a MAC address, which we call the router MAC address, and it's part of an extended community in the control plane. You guys know what I mean, right? No, you don't. I'm very cryptic, but let me show it here. When you do traditional routing, you have two switches. You put a cable between these two switches. It's an Ethernet cable. It's an Ethernet port. I put an IP address on one Ethernet port. I put an IP address on the other Ethernet port. Here it's Ethernet 2/1. And obviously, an Ethernet port is a MAC address, right? You all agree? Whenever there's Ethernet, there's somewhere a MAC address in there. And I just put an IP address on top of it. So between these two guys, I have ARP entries which are happening, right? Just very magically and automatically as there's some control plane over the top. You see also the host A, host C. I don't think they're very relevant, but when I want to show you where actually that router MAC comes into the play, it's actually the destination MAC of the remote router. So I have your next hop, but I don't know what your MAC is of that next hop. And why do I need to know that MAC? Because VXLAN is a layer 2 encapsulation. Even if I want to do routing, I have to properly populate the inner MAC headers of the VXLAN encapsulation. So instead of going and broadcasting ARP or ND across all my network, I'm giving you and serving you this MAC address, this router MAC address as part of the control plane, as part of an extended community. So here's the router MAC. How does it look in VXLAN? This is a classic Ethernet case right here. In VXLAN, it doesn't look different, but here, let's say the VTEP has a MAC address, and the VTEP has an IP address. And now the router MAC is, again, it's still exactly at the same point, right? It's kind of a transit segment. The magic point is the VTEP has the IP. It's not a point-to-point IP which I have to replicate multiple times. It's just in that underlay routing domain, and we're using that IP and that MAC address for the overlay communication in order to complete all of them. And now you see where the router MAC is. Let me see here. One more. It's exactly at the same part where you would have had it in the Ethernet part. Everyone got that? Yes? Yeah, no, it's late. Sorry about that. We're only here at Tuesday, so you guys will be probably fried till Friday, even with the party on... Party is Wednesday, right? I guess so. Packet walk for routing. I took the same control plane information. I took the same TOR, the same host to start with, but I go to another host as a destination. I go to host C. So it's a different IP subnet. So when I send my frame, my DMAC of that frame will not be the MAC address of host C, because host C is in a different IP subnet, right? The host already knows about that. And the host is a default route, so he uses the MAC address for the default route as the DMAC when he sends it out. And that's the signalization for me as a switch or a router to start routing. Tell me about where is that host C in that different subnet. So I will get that from the control plane. We have the L3 VNI, we have the destination IP, we have a host route for that. So we encapsulate based on all of these information. You remember this DMAC here? You see here the extended community, which is my router MAC. So I take this information, populate properly all the header information in the data plane encapsulation here, VXLAN, I need, and send it across to whatever the right destination IP is. In that case, it's TOR4. TOR4 takes this information, looks at its local tables, and sends it in the right VLAN space towards host C as an IP packet.
Question.
Sure.
How does TOR1 distinguish if the packet is routed or switched? Because host A is always getting the MAC address of TOR1 based on the anycast routing.
How does host A distinguish, or actually TOR1 distinguished if he needs to route or bridge? So actually it's not host A, TOR1 distinguishing that, it's host A distinguishing that. So when I have an IP configuration on my server, I have a subnet mask and an IP address, right? And if my destination IP address is not part of that segment I'm belonging to, I'm going to send it to the default gateway or to a routing entry I have. When I do that, when I send it to the default gateway, I need to encapsulate my Ethernet frame with the right destination MAC for that default gateway, which I have an ARP entry for on my host. Very good point. Very good. So when I bridge, so if host A bridges, the source IP address and the destination IP address is in the same subnet. At that point, host A will not take the default gateway, it will use the destination MAC to send it to. When the destination MAC is a host MAC and not the MAC of the router itself, in that case Tor1, then I will bridge. So it's all happening based on the destination MAC the host put in to the frame when it sends it out to Tor1. Yes?
Host A does not see the MAC address of host B.
In the bridging case, host A would see the MAC address of host B because there are broadcasts going around, right? It's a flat layer 2 segment. We can talk more about that. What about ARP resolution? We just talked about, yeah, let's bridge, yeah, let's route. It's all done, but at a point, you need to resolve ARP. So how does it work in such a network? So we have host A. Host A wants to know about, who do we have here? Host B, in that case. So he sends out an ARP request. And by the way, that's also giving a part of the answer you're looking for. So host A sends out an ARP broadcast. That ARP broadcast goes to the top of rack switch, Tor1, and he sees it's a broadcast. What do I do with a broadcast? Remember multi-destination traffic? All Fs, so we have to send it to everyone who is participating in that same layer 2 segment. I do a replication. I used multicast here. So if an all F or an all 255 reaches me as a Tor, I know it's multi-destination traffic. I look at my VNI, which is configured either with a multicast group or ingress replication. That's the unicast mode. And then as a destination IP, I cannot send it to just one because I don't know where he is. Where is he? So we just take the multi-destination replication, here's the multicast group, and send it to all the switches which are participating in that layer 2 segment. Everyone receives it. The ones which have VLAN 101 will decapsulate it and will send it as an Ethernet frame again out of the local area network ports. Again, the broadcast hits host B. And what does host B do as a good citizen? He does an ARP response. Now, ARP response is always unicast, switches to source-based, source MAC-based learning. So now Tor1 knows about host A, host B knows about Tor3, or vice versa. So we have some MAC address tables already populated as a result of that, and we're sending it back to the right point of return. Did we learn about host A? Yes, we did, because we sent an ARP broadcast, right? Our broadcast, MAC learning on the first switch, control plane updated, everyone knows where host A is. On return, nobody knew about host B. Host B responds, Tor3 learns about host B based on that ARP response, populates the control plane and sends it directly back where host A is, and that's how the ARP table is completed. Yes, please. Is it not efficient if the spine would populate this information? I could let the spine do that job. The problem is then the spine has to look at VXLAN, so I have to decapsulate and encapsulate again. That's a very difficult operation, by the way. There is, I think, one chip on the world which currently does it. What you do is there is something called ARP suppression. So once you did that operation for once, the ARP broadcast from host A will not be flooded through the whole network. It will be responded by Tor1 directly. So as soon as that learning happened once, we can take these information from the control plane, which is now pervasively populated, and answer as an impersonation of actually the host in there. And we're also doing refreshes for ARP entries. So if a host is once learned, and as long as he's there, or if he's moving around, we're trying to refresh him. So you always have MAC and IP combination fully populated in the control plane. There was another question I saw somewhere here.
How long will the other nodes keep the information that were
For how long will the other nodes keep that information? So depends on what information. The broadcasts, so the control plane information will stay until the host disappears. Right? So there is a host going away, then there is a MAC aging timer, there's an ARP timeout. This still applies 100% to the whole story. If you're talking about unknown ARP entries, they're not even making it. or incomplete ARP entries will not even make it in the control plane. If you're talking about how we keep the hosts in there, we're trying to do continuous ARP refresh. So if we know that your ARP table entry is expiring, we send you a unicast ARP. And per definition of ARP, you must respond to me. And as I'm the Anycast gateway on Tor 1, you will respond to me, and I will refresh my ARP table. And in addition to the ARP table, I will also refresh the MAC table. So the whole story of unknown unicast, flooding, or MAC is not there, ARP is there, or MAC is not there, but ARP is not there, will go away as a result. So we'll get way more efficient forwarding as a result in the whole fabric. Okay. So would it not be more efficient if the Tor would actively try to figure out when a host comes online? I'll show you how we do silent host discovery in a second. That's the next slide, which is coming up. It could, but there is one little problem. If there is a switch behind a switch, and that switch has the host, I will never know when a host comes online. So yes, I can do host port-based triggers, but it is not 100%. We have to somehow go in a way where we can get a 100% chance. If I'm changing your world of Ethernet and IP, and I give you 20,000 caveats, then you don't like my solution. But if I try to seamlessly integrate on how Ethernet worked and try to optimize on top of it with pieces and bits, then you will like my solution because the legacy Ethernet part, which was a pain, is going away, right? I'll take one more and then I have to continue, otherwise.
We just said, do the EVPN MAC addresses follow the aging hammer? So I have a remote MAC address learned by a type 2, but follow the aging hammer?
Yes, so EVPN always follows the local learning tables, right? So if you're connected to me as a switch, if you go away, it's my MAC aging timer which has to age out first, and then I will tell everyone in EVPN that you're gone.
So
right. Correct. It's absolutely. We have BGP updates, we have BGP adds, we have deletes, and we also have something like a sequence number when we're moving around in order to clear out all the information and update the new information. So it's same as Ethernet, but instead of waiting that everyone expires its timer, we're telling everyone that now it's the time to expire it. Okay. So let me go to a little bit about silent host discovery. Are they exist? I always have a fight with my dear friend, and he always says, there are no silent hosts, they're only dormant. So, well, you call it however you want, but there is a potential case where I don't know about host C. Host C is not in the control plane. He might be there from a MAC perspective, but if I want to come from host A, how do I reach a MAC in a remote subnet? And that's, so far nobody explained me that piece, it's impossible. So we do some magic. What we do is, we know that there is a subnet instantiated on some of my switches where that host C potentially sits in, right? I create an SVI, I put an IP on an SVI, I use that default gateway. So that SVI is there and that VLAN is there, because otherwise that host would never be connected to that switch, right? We would just want to wake him up. As a result of that, we're redistributing. Remember me talking about redistribute direct? So I take that SVI subnet, redistribute it in EVPN and that VRF. Now I have a routing entry. The little problem is that every switch who has that first hop gateway, as we use that distributed Anycast gateway, has that route. That means I have an ECMP route probably across 200 nodes in my network, which is a problem. So where do I send my packet now to? And that's why I decided that when I want to talk to this host 2101, I'm actually using the route which goes to Tor 2. And at that point, I would be dead in the water if I wouldn't have something cool in my back pocket. And that's how a switch operates when he receives a packet for a host he doesn't know about. So what does it do? The switch creates an ARP request, right? So now the switch gleans the information and actually sends out an ARP request. And it sends out that ARP request in the layer 2 segment, because we already knew it's a routed part, right? And we reached blue already, so we send out an ARP request in blue, but we send it out with the source MAC address of the first hop gateway. So the first hop gateway asks now, where is that host? As we have the same first hop gateway, the same IP address SVI for doing routing on all the switches where blue is, guess what happens? It will go to Tor 4, it will go to Tor 3, it will go to Tor 1, it will go to Tor 2, or Tor 2 send it out. But there's only one who actually has host C on it, right? So there's only at one point somebody will respond. And when he responds to the first hop gateway. And when I do this, what do I do when I do ARP learning? I change my entry and suddenly I have a host route. Before I followed based on an IP subnet, I find the destination subnet. I figured I don't know about the host. Tell me about the host, dear segment. We send it out to all the layer 2 VPN nodes which are part of that segment. Only one responded, host C, based on my request for the IP address of host C. Host C responds to the first hop gateway, and as it's a completed ARP request with that response, we're populating the control plane, and from then on, the control plane as populated will send it directly to Tor 4, where host C sits in. So you have a very short time of a non-efficiency. It's probably a couple of, less of a second, I would say. I didn't want to say millisecond, but a couple of seconds where you potentially send to the wrong node, but we clean that by updating the control plane and avoid unknown unicast flooding. There was a question over there. Yes, correct. So where do we flood to, right? Yes.
Then your query earlier around 3001 to a VLAN versus 3001 to multiple.
Correct. Okay. So does it have any relation to VLAN aware versus VLAN base? No, it does not. That's pure in the control plane. So it purely takes blue, local VLAN, mapped to a VNI layer 2, has a BUM replication mode, either ingress or, and that's based on that, we are sending it to them, right? To all of them. We don't know where he sits, right? So we just do a broadcast, unknown unicast, or multicast forwarding in that case, so BUM in this. So you heard me talking a lot about this SVI and first hop gateway, and that's why I said in the beginning, I thought there is a missing section. Because that first hop gateway, yes, it's covered in IRB, but it's only a part of it, right? It's only a standard part. What does this first hop gateway mean, and where is it, and what does it? And we call it distributed anycast gateway. It uses an anycast approach, so it's the same MAC address and same IP address for a given subnet on all the switches. Okay, so it's a pervasive gateway approach. What does it mean? When we look at all these switches, let's assume all of these switches have VLAN 101 on it, and I want to do routing to another VLAN, to another subnet to be correct, not VLAN, but you guys are getting me, right? So I put that host-facing local to wherever I attach my endpoints. Now I do another one, I put here blue as well. So you see now SVI 101, SVI 202, respectively for VLAN 101, VLAN 202, and then respectively to L2 VNI 3001, 3002, which I used through the presentation. And both of them have on all of these switches the same IP address. And at the same time, across all of them, the same MAC address. Because guess what? When you do host mobility, if you change the MAC address, the host has to refresh its ARP table for the default gateway, and that's a mess. Because that will result in black holing. So we keep that pervasive gateway there, and it's an all-active approach. So there's no HSRP hellos going around or VRRP or any state replication or such. It's being all-active anycast. And anycast as a terminology means one to the nearest. This is how the configuration look. You see the Anycast gateway MAC, which are configure switch global, and then you see the VLANs with the SVI, the SVI respectively to the VLAN with the IP address for the first hop, and you see there I'm calling him an Anycast gateway, and at that point it's just active everywhere, and it is not advertised to the fabric. It's only present host facing. Because think of when every switch advertises this same IP, same MAC up into VXLAN EVPN, what would happen? You're there, no you're there, no you're there, no you're there. Duplicate detection, not a good idea, right? So we do that host facing, and that's actually magic, which all Anycast approaches do. They are the same everywhere, and they're only exposed to a place where they exist alone. Or you use a routing protocol with equal cost multipath. One to the nearest, so host A will always use its default gateway where he is attached to. And host C, the same. They will always use the default gateway, which is as local as possible, which allows me to not need to flood host-facing ARP requests for the default gateway to the whole fabric. And the other thing is, I don't need a layer 2 segment to find somewhere a default gateway which runs with HSRP or something like that. No more hairpinning. You guys remember that thing where you have to go through the whole network, find the default gateway, and then you go all the way back layer 2. And if somewhere a link flaps, you have a spanning tree mess going around. So we're going host to host, closest to the host, closest to the source host, closest to the destination host, routing and bridging. No diversion. I give you the fastest path. We tried the same with OSPF, right? Shortest path first. We do the same here. We try to give you the shortest path from one host to the other host. So that means we also have to do some magic when we move. So when you move host C, we have to clean the ARP entry on the old location. We have to update the ARP entry on the new location. Same thing for the MAC entries. And we're doing this in the background. EVPN does a very fantastic job for this. Now, good. I was saying that we should have some dual attached hosts, and I only showed you single attached hosts. This default gateway approach also works for dual attached hosts. Why? Because a port channel hashes bump traffic only to one of the member ports and not to all. That means the host sees one gateway, right, per VLAN. He can balance per VLAN, and we don't have any issues on duplicates or such. And we have a default gateway which is active. No more hellos in between. Oh, who is active, who is not? Oh, he dies. BFD has to signal over. Oh, we have to make sure ARP is there. We take care with EVPN and the distributed Anycast gateway and the respective IRB implementation to make this happen. So this is the ARP request and response. And I think that's a fantastic segue to talk a little bit about VPC. Everyone still good? Nobody left? Normally they left after 1 hour, and then we have a happy camping with like 3-4 people till the end. No, just kidding. Question?
The magic that you described, is it based on the RFCs and standards, or is it something Cisco proprietary?
Okay. Is the magic for the move logic based on the standard or Cisco proprietary? It is based on ARP at first. So a move signalization is either signalized by reverse ARP or by GARP. Now, the GARP piece is simple because GARP has IP and MAC in there. That's very easily and pervasively standardized how you do that because you just take the GARP and update. The reverse ARP part is a little bit more difficult because there is no MAC in there. By the way, if you want to go and look what reverse ARP is, check the Wikipedia entry. It says it's an obsolete protocol, but it's still very, very aware in all the virtualization layers these days. Not saying any name. To the reverse ARP piece. The EVPN standard defines the MAC move to a certain extent, but it doesn't entirely tells you how you have to update the ARP tables of all the other switches or the new switch where your host sits. So we have probably around 8 to 10 years now where we do something like host-based routing and this control plane interaction. We only had reverse ARP in the beginning, so we created a couple of mechanics we are doing in order to address all the corner cases. So that's the Cisco magic which we put in. I know of cases where reverse ARPs are not properly aged out after a move. Not saying that others cannot do it, but I know of some cases. Sorry, some marketing has to be. They give me a marketing title somewhere in my thingy. All right, VPC. I know you guys are probably bored, and some of you say, he's talking about VPC. Why are we not talking about EVPN multi-homing? EVPN has an MCLAC approach, which is also called MAC multipathing, and it has a slight burden to the hardware which you need in order to do this, and it burns also a lot of ECMP indexes. So we decided that instead of burning MAC ECMP indexes, we keep them for IP ECMP, and therefore give you a lot of wide ECMP for our routing approach, and we're using another approach for the multi-homing of hosts. And we use a similar approach as what I just before explained with the Anycast to the host. It always looks the same, doesn't matter where you go, right? We just do that the opposite, where we say multiple switches have the same VTAP address. What does it mean? Short recap, this is how VPC is. There's a peer link, we have a peer keep alive, there's a VPC port channel, we have orphan ports, there's a VPC domain. When I say VPC, it's the port channel, right? When I say orphan, it's the single attached. VPC domain, it's the construct. Peer link and peer keep alive are two mechanics there. Now, what I do is, where is it? Actually, I didn't want this one. What I do here is nothing else than dual homing of these hosts, and as that domain exists, across that domain, I define a common shared information, right, between these two members, and I use individual information. So from a router ID, from a BGP side, I have two identities. I'm kind of schizophrenic. From a data plane, I'm one. So the same MAC address is being advertised from two different router IDs, or route distinguishers in that sense, but with the same next hop. So this is basically what's going to happen here. And I don't know why this is not moving forward. Here we go. Come on. Yeah, that's not what I want. Here we go. So when that host is connected to that VPC domain, he will send its own MAC address and will define the next hop as what we call that Anycast VTAP IP address. So it's the same IP address for both. It's actually only the secondary IP address for both. And that's what that diagram here and the one which comes right after that a little bit better explains. Control plane-wise, separate. VPC was always control plane-wise two separate entities. From a data plane, is it a port channel to the host side, or here for the VXLAN fabric, it's a sharing an identity. And this is the config, or this is the information you're looking for. We're using a virtual IP on which is shared between these two nodes. And from a config, to give you a little bit more of meat here, the loopback 0 we use as router peerings, because we need to have individual router peerings. And down there you have a loopback 1, which is impersonating this shared common piece there, which is the secondary IP address, which is the Anycast IP address. Now you'll also see here I have 3 different hosts attached, because I want to tell you a little bit about how we're advertising these hosts. And then you can throw tomatoes on X, because, hey, that's inefficient, we don't like that. Let me see. So when you look at this little table on the bottom right, you see there on the very bottom, type 2, a host. So it doesn't matter if it is an orphan or if it's a VPC. We always use the VIP. Now, it's great that we always use the VIP, because it goes to the wrong side. We use the peer link to deliver it to the right. It's an efficiency, right? You guys don't like the inefficiencies. We said we want to make it more efficient. Same thing for routes. We always send everything to the VIP, because that's the only construct we have there. And it's unfortunate. So this is how it looks. Control plane update, Tor 3, Tor 4, building a VPC domain. My Anycast VTAP is represented with the VIP 10, 200, 200, 1, 2, 3. So if host A wants to send to host B, it will craft that packet, it will send it to Tor 1. Tor 1 is going to consult the control plane or the data plane, depending where the entry is, and will decide, I send it to 1, 2, 3. to the virtual IP, right? Which path are we going to use? Anyone? All. Can go left, can go right, which is great for a VPC and dual attached host. But what are we doing with the orphans? Slight inefficiency at that point, right? Anyone an idea? Correct. We go over the peer link for the traffic. You don't care on that. Is that okay for you? Okay. So somebody wants a bounce entry over VXLAN, going over the top? Well, let's see. Again, recap. We have a peer link, right? Or we remove the peer link and do it over a virtual peer link over a tunnel. So this is what we're going to do in a 9.2.3 release. It's orange because it's not yet released, okay? So this is coming. This is somewhere in this quarter, calendar year. But I wanted to take the opportunity to talk a little bit about this because there are like 2-3 things in there which I consider to be an efficiency gain you're getting out of VPC. One of the additional key criteria we had why we decided to use VPC is convergence, scale, and keeping all the existing VPC features you had in the past, unicast, multicast, etc., and just giving you a little bit of more efficient version, and that's what we're doing here. We could have gone EVPN multi-homing and do all the MAC multipathing, but multicast would have come somewhere in a year, or somewhere in 2 years. And what are we doing with all these applications there? So we had to make a decision on that side. So we're removing the physical peer link, and we're doing a virtual peer link. You're putting 2 loopbacks on each of the switches, and they find each other. We still keep the peer keep alive. You can put it over the fabric if you want. It's your resiliency discussion, or you put it over a separate network out of band. You have that option there, and this is what I wrote down here in this slide, so you have all of these different options there. One additional thing we're doing, as I said, we have individual identities already for the control plane, and we have a shared identity for the VPC domain. We're actually going to change how we advertise hosts, specifically how we advertise VPC attached host and orphans. So your point of going over the peer link doesn't work anymore because there is no peer link. So what we're doing is actually for the VPC attached, so whenever there's a port channel and the VPC command on that port channel, we will use the VIP because it's dual attached. If it's not attached to a VPC, it's an orphan port, so we will advertise it from the individual identity. So the tromboning over the peer link, which we just discussed, will not happen anymore. And on top of that, if an orphan port or an orphan host wants to talk to an orphan host, we will not use the virtual peer link, we will use VXLAN EVPN-based forwarding. So your troubleshooting becomes easier on how left to right is actually communicating, and the same thing happens for all the routes. Some of you might have heard of what we call advertised PIP, where we use a type 5 and advertise it from the individual IP address. But when you had the peer link, you still had to do a per VRF peering over the peer link in order to exchange routing tables. That is gone as well because orphan network to orphan network will communicate over the fabric as it would be subnet to subnet on individual VTEPs. One sec, there was a question back there. Very good question. What happens if the VPC port channel fails from one link? Let's assume my traffic hashed to VPC1 from the fabric side, right? And my port channel member from the VPC host to VPC1 fails, right? So traffic at that point in time would still go to the 123 address, it will still go to VPC1, but at that point we have a bounce entry which exchange the traffic over that virtual peer link to the other side and will be delivered. We're not changing a VPC attached host between VIP and PIP because that's control plane churn, which means you have to change a lot of things in your network. Sometimes you want stability, right? And even in a failure case, we want to reduce the impact, the blast radius of whatever actions are happening there. So we have a bounce entry there for the time being of the failure. There was another question here.
How does this affect the scalability of the fabric? Because the number of MV peers is going to increase a lot if you have...
It's a very good question. So there is an increase in NVE peers. So today we officially support 256 NVE peers, or VTEP neighbors, is quite a large number. In this case, it is actually true that these are 3 VTEPs now. Before it was 1 when we only had 1 IP address. We're going to address that. Our hardware platform can go way beyond 256. In our early hardware platform which we used, we had a hard limit on the hardware implementation of a chip which we acquired. In our chips, we don't have that. We actually have a very significant number there. So you will see in the subsequent release after the 923 that we give you back to 256, regardless if you use VPC with 3 VTEP or 1 VTEP. So you will see a gain there. I don't want to do too much marketing and selling roadmap, but we understand implication of what we're doing, so we are addressing the implication in subset scale addressing.
Can we seamlessly moving from physical peer links to
Can we move seamlessly from physical peer link to virtual peer link? There is a method we are doing. We're sharing that as soon as we completed all this. Right now, we're exactly at these testing on what is the most seamless approach. There are various ways of doing it. One has a little bit more impact, the other one is a little bit less, but it looks good. It looks good. Just to repeat here, I was talking about orphan attached networks or VPC attached networks. A route type 5 will always be advertised with PIP, and that's where we want to have our ECMP indexes used rather than for the MAC address. And you see here, type 5 IP prefix route, VPC is WIP, VPC is PIP, orphan is PIP. So you basically get now the same behavior we had for routing before for bridging. How do we communicate from subnet X to subnet Y? We use the VXLAN fabric as it would be 2 completely individual leaves. So you're going back to having a more loosely coupled approach than the very tightly coupled approach which we had today with the peer link and the VIP approach there. A little bit about orphan host packet warning. I said I want to give you an idea here of how this goes. This is an orphan. I have an orphan host advertised. You see there host B1, and you see it's coming from Tor 3 or the IP address 103. So I will send the traffic directly to 103, which is the most optimal path I'm having. And similarly, sorry, let me go one forward. And similarly, when I want to go to B2, which would be behind Tor 4 or IP address 104, it will go directly. This clicker is, I think my batteries are going and dying. Similarly, it's going right away to Tor, which one is it? Tor 4, where host B2 is respectively attached. So we're giving you the best of both worlds, right? Saving some resources on one side, giving you some optimization on the other side, and that's how we're continuing to the journey of EVPN since we started somewhere in probably 2014, 2013 with the first release which we brought out. So we're quite some down the journey and saw certain things from our dear customer on what to address and what to fix. We're not done. I don't know why it clicks twice when I push once. So we have 3 more topics. Underlay consideration, I think it's key. When you go into VXLAN papers, you always talk and read about NCAP, VNI, and all of this kind of stuff, but nobody tells you how to build your network underneath to be efficient, resilient, and so on and so forth. So I think we should spend a couple of minutes there. Let me see. Yeah, we're good in time. So first thing, it is an overlay. So it serves on top of your underlay, right? And that gives me an overhead. That overhead has to be addressed. So we have to do something at the MTU level, right? So VXLAN has 50 or 55 byte, 50 or 54 byte overhead, right? Where are these 4 byte coming from? There is a way to preserve the inner .1 queue, so that's additional 4 bytes. Otherwise, you just have 1550. Don't be shy with the MTU part. If your transport network is your own network, don't be too shy to crank up that MTU to accommodate this. Maybe you have at the time a double NCAP approach you want to do, or you have a double tagging approach you want to accommodate. So I would always go at least with 1555 if you're sure you're only going double tagging. If you go beyond that, And also you have the requirement for jumbo MTU. Maybe you have some iSCSI or some other kind of storage application or other server application which require a 9,000 byte frame. At that point, you have to look at what your switch is capable to do. In general, the NICs, the server NICs, are normally around capped at 9,000. Our switches normally do 9,216, so that should be enough to accommodate a lot of tagging for the overhead. So 9,216 is a good approach to do. I'm not saying you must do it. The importance is that every interface which has to transport these 9,000 bytes has to be set to this. So you have an access port, right? Trunk port, for example, 9,000. If you want to do routing, you have an SVI, has support 9,000, right? My uplink has 9,000 plus NCAP, has to do 9,050 or 55 or 54. So think of this. In VPC, if you have a physical peer link needs to accommodate what? The additional 9,000 at least, right, when you want to do this. So just make sure that your path is working with that increased MTU. I had a lot of troubleshooting. I don't want to put anyone on the spot, but a lot of troubleshooting where in steady state everything worked fine. And then somewhere a link failed, and suddenly certain packets didn't work anymore. So, okay, must be somewhere an MTU mismatch in the fabric, on a peer link, on an SVI or so. So be aware of this and make that consideration on the very beginning there. There's one platform in our portfolio, which is the Nexus 5600. It's been in the years. It does VXLAN, EVPN. But for example, that platform would not be able to do 9.2.16, as there is an internal header we are using, and that will bring us to 9.1.9.2. So look at consistent kind of MTU setting across the platforms you're using. Makes your life easier and troubleshooting respectively yourself. So it's not my phone. So no fragmentation needed, because what you don't want is to be the switch, and at the same you have to do fragmentation and reassembly, and then you have these 100 gigs uplink or 40 gigs uplink, and you figure you only have a couple of 100 megs because you are not going fast enough in that fragmentation and reassembly approach. So avoid fragmentation at all. The other thing is called interface principles. I mentioned in the very beginning, I said, try to do no switch port first. So make a layer 3 interface between your leaf and your spine, or between your edge device or your intermediates. No SVIs and trunk, because you're just creating another layer 2 domain there, and you have to take care on all these pieces. So do a layer 3 interface, no switch port first. Do a point-to-point. You can also do IP unnumbered. We have both approach, and you will see later that we are using IPv6 link local for VXLAN in a little bit later this year, which will, I think it will kick ass when you don't have to put any IP addresses anymore for all these point-to-points. For the loopback, for the NVE, for the VTEP itself, use a loopback. Always use a loopback. There's no other way. We want you to use a loopback, because a loopback never goes down, right? It's always reachable over a routing protocol, so that's a good thing. There's also consideration on how you separate certain things, and that's where I normally try to give you a little bit of good practices on what I learned in my earlier life for operation of MPLS networks and similar, which is how do I identify an IP address, what its purpose is. I'm not telling you you have to do it. It's just, for me, it's very, very easier. So I'm trying to create an addressing plan. I'm trying to create separate aggregates or subnet chunks for separate functions. VTEP is a function, right? So I'm giving them a distinct address. And the control plane presence is another function, so the route distinguisher, for example. So I give them a distinct address. Now, in my world, the VTEP, loopback IP address, and the routing identifier, or the RD, has always the same last octet, while the previous 3 octets are different. So in here, you see here a 10110. My first VTEP would be 10111 for the route distinguisher, and would be 10.200.201 for the data plane. So when I go and sniff, I know exactly what I filter for and what I'm looking at in order to identify is it control plane traffic, data plane traffic, etc. and so forth. Again, you don't have to do that. Point-to-point, I aggregate a chunk. Sometimes if I have 4 spine, I use 10, 1, 10.1 for the first spine, 10.1.2, 10.1.3, 10.1.4, so I know exactly which link has what subnet for the respective spine. It can give some sanity, but you can drive it to the insanity of IP addressing and having fun here. It's just some ideas there. And as said, the underlay today is IPv4 only, but IPv6 to show up pretty soon in the similar theater. I'm waiting for the tomatoes. Anyone wants to do BGP underlay? Nobody? Come on, at least one. I did all that work.
Ask people from my boss.
Who?
My boss.
Your boss? Okay. Let me give you some arguments. By the way, I'm a big fan of somebody who wrote an RFC, an informational RFC about how to build large-scale BGP networks. It's an awesome draft. But have you found a single line which talks about an overlay or a BGP-based control plane for an overlay in addition? If you find it, send it to me. I send you something back. I read it every day and I still haven't found it. Regardless, OSPF or ISIS, an IGP is very simple, right? You put an IP address, you put the router instance on top of that interface, and these things just, they work somehow, right? And your OSPF or your ISIS, your IGP you use for that underlay fabric, it's a couple of routes, right? It's a couple of host routes for the loopback. It's a couple of point-to-points. So it's not massive. But even if it's not massive, and I'm not scared of any of these OSPF or ISIS domain sizes, I always use a single area. I never haven't ever used a multi-area in these cases, neither on ISIS nor on OSPF. What I would look at is make sure it's point-to-point. OSPF has that DR-BDR election. It takes a hell of time, and it's overhead. Also, your LSA types become suddenly being multiple different ones. So when you do the interface being point-to-point or the network type point-to-point for OSPF, you create a little bit sanity and you reduce the amount of overhead OSPF introduce on its own protocol, because you don't want a broadcast segment, you want to have a point-to-point segment there. On the ISIS side, I do understand not everyone understands CLNS, me neither. But it's actually a pretty cool protocol, which is IP independent. And now, if you ever deploy a V4 network today and want to go to V6, ISIS is magic because you just add another IP address on it, an IPv6, and you don't have to change the protocol. What happens in OSPF, when you do V4, you have a V2 version. When you want to go to V6, you have to add OSPF V3. Okay, you're running now 3 routing protocols. You want to retire one at a point in time, V2, keep V3 in there. So these are kind of considerations you have to make. But the deployment simplicity that you don't have to configure a static neighbor peering, the simplicity of these IGPs in a confined area is actually something which brings a big advantage. Plus, link cost awareness. How are we doing this in BGP? You go and tune the metrics, or you're taking some extended communities or something like this. That's where the IGP comes in. And if you have leaf spine, you have kind of a uniformity, you want native ECMP in there. It just solves a lot of pain, how you have to think in these areas. One cool thing in ISIS is, if you have a link flap, it doesn't mean you have a full topology recalculation. ISIS doesn't has an overload of topology and network, while OSPF does. Right? So if you have a link flap, OSPF will do a full SPF calculation across everything, while in ISIS you don't. Okay? So these are kind of blast radius and failure scenarios. Is it a concern? Our devices today have CPU, which is probably 50,000 times as fast as what was there when OSPF or ISIS was written. So it's not a real concern. Again, it's having sanity or potential reduction of blast radius in corner cases to your network. I clicked, so I try again. I'm going to talk about it. I'm sure there are a couple of people in there which are interested. They're just shy to raise their hands. I'm okay with that. I'm not flaming you guys if you liked it. So you can use eBGP for an underlay. But the eBGP and the underlay will have an implication to EVPN in the overlay. Okay? Why? VPN address families consider always iBGP as baseline. Because the edge device where the tap is, that's where the logic is, and the tunnel goes to the way destination. So that's how eBGP works, right? It's a next hop unchanged, if you want. So next hop's not self, right? The next hop is my neighbor there. Now, when I use eBGP, what happens? The next hop is always my neighbor. Is my spine a VTAP? So you have to tell the spine, by the way, if you get EVPN control plane information, you're not a next hop. So that results in additional configuration. In addition to this, there are two different modes on how you can implement your eBGP story. You can use two ASs, I'm going to show you that, or you can use multi-AS. The reason why I call it two AS or multi-AS, because I don't consider that as true eBGP, at least not for the overlay. For the underlay, yes, you do a true eBGP, at least in the multi-AS case, where you're basically reinventing the internet in your data center. That's fine, it's okay. I said metrics is kind of a thing. BGP is a path vector protocol. So the only thing it knows for hops by hops by hops is ASs. Think of this. And it has a loop protection mechanic, which is based on AS path. Let's look at this. I have my two AS design. All my spines are in the same AS. All my leaves are in the same AS. So if my switch here wants to talk to a host on this switch here, what will happen? Nothing, because you will not even install that route, because it's the same source and destination AS. So you have to go and tweak and actually disable the loop protection. So there are two modes. One is AS override, the other one is allow AS in, which allows you to have your same AS in the path being there. So you need to go and tweak this. Second thing is, ever heard of an eBGP route reflector? It doesn't exist. That's another speciality in VPN address families. A VPN address family only installs routes in two cases. Either you're a route reflector, let me recap. An eVPN address family only advertises routes beyond one hop in two cases. You're a route reflector, or the VPN is instantiated on yourself. Otherwise, you don't send it further. Now, this spine here is not a route reflector because that doesn't exist in eBGP, right? So I have to tell that spine to take all the control plane information he got and send it out to all the others. I don't want to install all the VRFs up there, right? I don't want to import and export all of this. So there's something called retained route target, where basically we move that spine into a route server, which is the official terminology for an eBGP route reflector, if you want to call it this way. So in this case, you already had to configure two knobs and just make it work. Now, there are also a couple of other cases. I don't want to go down there, but there's a whole enchilada of things you have to consider. For example, do you want to have all spines being route server? Yes, no, two are enough, like route reflector? You choose. You just have to consider you send for every reflector, is it E or I BGP, you send another copy and all the leaves have to run test path against that. So a route which was previously 1 can suddenly become 4 in this case. Just CPU again, right? It's blast radius and so on and so forth. The other thing which is happening is we have to take care on the overlay. As said, we have now different ASs. My neighbor has a different AS. That means it's my next hop. So I have to tell next hop unchanged on my spines, and so on and so forth. So same thing, disable BGP AS check because my leaf-to-leaf communication is in the same AS. You can do it. We wrote a blog about it. There's actually everything described on how you do these things. Now, if all my spines are route reflector, I can use the same BGP peering for underlay and overlay, right? I do my point-to-point, right? Now, I go back to my 90,000 MAC addresses in the control plane for the overlay, and I go back to my couple of hundred routes in the underlay. What happens if a link between leaf and spine flaps? It's not only my underlay going down, it's also my overlay going down, and I have a churn of 90,000 routes in my whole network. Now, we are recommending there to have a loopback for the EVPN peering and use point-to-point for the underlay peering for the IPv4 unicast. So in a case a link fails, your loopback-to-loopback communication doesn't go down, right? It stays up. So no churn in EVPN, only churn in your underlay with a couple of hundred routes. That keeps your network steady and stable. Multi-AS is not, multi-AS is not very different. I should have changed the title, copy-paste filler, thank you. Multi-AS is not very different. The difference in its main essence is that I don't have to care that much for the underlay because every leaf has its own AS, so at least the underlay works. But I still have the same consideration for the overlay because the next hop change is there, so I have to make a next hop unchange, retain route target, and so on and so forth. So it's still a couple of knobs to turn. It's still the 2 BGP peering, which I would recommend to do, different from underlay, IPv4 unicast, and EVPN overlay loopback to loopback in order to get that done. You have to think about what is the advantage of what I'm getting here, and most of the times the answer is I run a single protocol. Yes, you run a single protocol, you only have to troubleshoot a single protocol, it's BGP. But guys, IBGP and eBGP is very, very different. And we add MPBGP with address families to it. Yes, it's called BGP, but some of the functions you're actually using there and transporting there is still different. So IPv4 unicast address family is probably what you guys know most. Internet peering, some per VRF peering. Don't compare it one-on-one with what EVPN is. Question?
Are there any implications with this setup with the functionality of the VPC?
Is there any implication with VPC? Yes, there is. You have to make a decision on if your VPC complex or your VPC domain is in the same AS or in a different AS. And then remember, if it's in a different AS, you do IBGP between the VPC members. That means that link is not an additional cost. So when you look at it from the remote side, using the peer link has the same length as going directly, which is another disadvantage you have to consider there. Yeah, there's a whole enchilada. We can talk for the next 2 hours only about this. You guys want to have an eBGP session? No. Okay. Let's go forward. Again, I already mentioned that underlay and overlay separated. I put it in for reference. And remember, BGP doesn't do ECMP per default. You have to tell them to do it. And when you don't tell them, you don't have ECMP, which means you have convergence. On a routing failure, everything starts calculating. So we're talking about 3 to 10 seconds versus 3 to 0 seconds convergence for packet loss when we look at this. Little bit of TRM. Anyone having a multicast use case in the overlay? 1, 2, 3, 4? Okay. There's a problem in VXLAN I alluded to initially, and it is that multicast is being treated as broadcast down on unicast and multicast. That means if a source and a receiver hanging on Tor 1, yes, I can do this, but I will also send that same multicast traffic everywhere else, right? It's like the dog going to the park and peeing at every next tree, right? So we don't like that much. So it's an inefficient forwarding approach because it goes everywhere. It leaks, pretty much, right? Now, we can do a little bit better. Sorry, I'm having some issue with the clicker. Here we go. We can IGMP snooping. Now, IGMP snooping is a local switch feature. So that's good. So as long as source and receiver is local, IGMP snooping is great. Don't forget IGMP querier or an SVI, which has PIM enabled in order to relay the DR function there. Now that's great. But now when we have a receiver also across the fabric, you remember I said it's handled like BUM, so we replicate it to every VTEP which is participating in that ingress or BUM replication group in multicast. So we send it to every VTEP which participated in that layer 2 segment. So again, we're leaking. This leaking stuff is not nice. Don't like it. You guys like that kind of behavior? Yes? No? Don't care? Well, let's see what else we have. How do we routing? Again, VXLAN is layer 2. EVPN has no awareness of multicast, so what will we do? We put a router on a stick somewhere which does multicast routing. Now you see this IP address up there, this 10.10.254, 10.10.10.254. This is not my default gateway. My default gateway would be 10.10.10.1. And similarly, it would not be 10.20.20.254, it would be 10.20.21. So my unicast first hop gateway is on all the leaves, and my multicast first hop router is outside on a stick. It's easy, right? Nobody thought about that. Now, we were talking about leaking, so we again send it everywhere to reach that first hop router in multicast. So we do a little bit of routing, multicast routing, and then we send it back to all the switches again, and finally send it to the receiver which actually wants it. And this is how it looks from the amount of traffic I'm actually generating. I'm creating everything twice. So the story of single copy before, which was in the layer 2, that was great, but now we replicate it in the other layer 2 through that router. So we went back to an inefficiency. Don't like. And that's where we said we have to do something. We had a very smart person. His name is Ali Sajasi. He wrote all of the EVPN drafts, or I call him the godfather of EVPN. Yeah, I think it's more the father of EVPN, to be honest. And we came up with a seamless integration between MVPN and EVPN. So we use MVPN, or specifically NGMVPN, for multicast control plane, and we're using EVPN for unicast L2, L3. Why didn't we just add a lot of additional functions to Ethernet VPN? Have you guys looked at what multicast is already in Ethernet VPN? There are already 3 route types which are doing the multicast bridging and IGMP snooping and synchronization thing. So we wanted to be a little bit faster than creating a new draft and going through iteration. And MVPN is there, and the seamless integration is actually already being described and already being filed. So that's what we're doing. And this is that nice MVPN seamless interop draft, where we're using, again, a distributed Anycast gateway, this time for multicast. So you saw that router on a stick. We don't need that anymore. We don't need an additional IP address in that segment. Now every switch has the distributed Anycast gateway with that SVI, that IP address, and we just enable multicast on top of it. We need some transport, so we use multicast in the underlay for transporting this information. It's on a per VRF base, so you have a multicast VPN now, right? You have a layer 2 VPN, a layer 3 VPN, now you have a multicast VPN. In the overlay, again, we specifically use NGM VPN, which I think it's RFC 6514, 6513, somewhere in that area. And that's exactly the message encoding we do. We just use a VXLAN endcap other than an MPLS or a GRE endcap, which is also being possible there. And if your switch doesn't talk TRM or tenant routed multicast, we can even interrupt with them. Is it in messaging over EVPN, multicast signaling, or over encapsulated IGMP? So this is the pain, right? When you need a solution, but you know exactly it takes 3 years until you have it finalized as a standard, you have to do something. That was, by the way, how EVPN evolved as well, and that's why we have different options as different opinions and things arise. TRM, as said, uses a control and data plane integration. I tried to put some information in these slides. I think it's a hell of slides just about this, but I want to give you a little bit of insights. So the first thing is, in light blue, that's your underlay. You see that every VTAP is participating in a source tree, and they're ready. They're ready to transport multicast, right? And you see that that source tree is actually associated with a layer 3 VPN, an IP VPN or a multicast VPN in that case. And you see my sources and my receivers connecting to these DRs. So it's a totally distributed multicast routing approach, or multicast host routing approach, if you want to. If a source announces itself, we tell the control plane, service is active. There is a source and this group. Now, remember this whole rendezvous point stuff and so on. There are 3 different implementations of rendezvous point and so on and so forth. I'm going into a mode where every of these access switches is a rendezvous point. That means we don't have star, G entries. We only go with S, Gs. which means you don't double the multicast state in your fabric there. So again, he sends it to the control plane. At that point in time, there is no traffic flowing. It's just control plane knowing there is a service active. And at the point where we actually have a receiver coming online, he will join that source tree immediately because his RP is directly a switch itself. So we pull that information, we instantiate the state, and we're going to replicate multicast. Now, this slide is not wrong. We will send it to all the participants of the MVPN right now. We're only having a SPIMS implementation, means we have one single tree. What you will see subsequent is we will have multiple trees specific on the flows, so we're not leaking to these intermediate switches which you're seeing there, but only to source and to destination. I know you guys are probably tired and somebody will kick me out soon, so I'm going to make sure that I'm not rushing, but giving you the gist of it. We always do a local and remote snooping with TRM. So we have kind of an IGMP proxy mode if you want, so not yet MLD, but an IGMP proxy mode, which allows me to more efficiently send traffic and signalize these information in the EVPN control plane as, I think that's a type 6, if I'm not completely mistaken, in EVPN. So we try to avoid unnecessary forwarding of layer 2 multicast traffic, or it's not layer 2 multicast traffic, it is multicast traffic in the same layer 2 segment, as layer 2 multicast is different than IP multicast in the bridge segment. So that's what we're doing here. And then on top of that, we use in TRM, when we use the L3 mode, always routing. Even between hosts in the same subnet, we always use routing. We have an infrastructure tree which is there. It's being called the default MDT as per the standard. That's kind of the group which is associated to the VRF. And you see that here with the L3 VNI being up there. If we have sources, receivers all over the place, we always route. So that means we do a local routing, we do a remote routing, and we're only pulling the trees where necessary. So we're not sending it to all the front-facing ports if we don't need it. We only replicate it from the spines to the leaves at that point, and I hope you have enough bandwidth to a big extent in there. What else do we have here? So these text pieces, these are for your reference. I thought that when you have the PDF, you don't have to listen to me again. You can just read it, and then we're going forward. The other thing to mention is, as we always route, we are true to ourselves. If you route, you decrement the TTL. You guys agree? Is this a good practice, or should we just fake something and don't tell you and let loops happening? So we don't. So we are true to ourselves. We do a routing approach. So we decrement the TTL if you go from one host to the other host of over the fabric. We understand there are some applications which require a TTL of 0, more bridging approach. We have a way to address that. You will see this being available when you reach out to us. Very last section, couple of slides. Tomorrow morning, there is another session, 8:30. It's talking about multi-site, the DCI part. I wanted to give you a little bit of a segue in there. So first, VXLAN was an NCAP. Then we added control plane for intra-DC. And everyone built local data centers. And then somebody had that glorious idea to stretch VXLAN tunnels all over the place. And that means your nicely created 3-tier hierarchy becomes, from an overlay perspective, a flat single fabric data center, right? So you remember, the tunnel is over the top. He doesn't know how many hops are there. So it's flat. So this is something which means no DCI. This means this is a single fabric. You can structure it and add multiple ASs as much as you want. It's a single overlay fabric. And this is exactly what this little guy here tells me. Scaling is an issue, because all the VTEP neighbors have to be considered. It's a full mesh, everyone to everyone. You have to a stretched multicast tree or BUM replication. You have a single protocol. You have no abstraction in the underlay there. And you have no way to prevent any control plane propagation, because we need this information. It's one fabric. So we did some work about a little bit more than a year ago. I think it was like 18 months. and we invested into making VXLAN DCI capable. We had a new chip, and the new chip had the capability to terminate VXLAN and re-encapsulate VXLAN. Now you guys say, God, that's easy. For L3, it's very easy. It's called RIOT, routing in and out of the tunnel. Do it for layer 2. Split horizon, broadcast prevention, loop prevention, and so on and so forth. So that's where we invested in, and we created what we call multi-site. So in multi-site, we have the ability to show you the same hierarchy you have in the underlay into the overlay by saying you have a local VXLAN domain, and you stitch that local VXLAN domain together with a remote VXLAN domain. So you build multiple kind of these sites, and you stitch them together, and that gives you multiple logical data centers, right? So we're back to the proper DCI, to the availability zone, as you might have heard there, and this is how it looks like, right? So we have my overlay inside 1, and my overlay inside N. We can go widely there, and we have that multi-site overlay stitching them together. Again, we impersonate a whole fabric with a single IP address. So for site N, all VTAPs inside 1 is one address, and that's the address of these 2 BGWs up there, which we call border gateways. So this is the stitching point of VXLAN to VXLAN tunnels. And the session tomorrow, it's 2 hours only about this story there, which means that whatever is in my sites is completely hidden and could be any kind of VTAP as you wish. Also, for broadcast down and unicast and multicast replication, there are 2 different domains, right? It's site 1 and site N. They don't know of each other. So they can use, one can use ingress replication, the other one can use multicast, one PIM BIDIR, the other one PIM ASM. So they don't know of each other, so I have to separate them. What I do, I stitch them together over that blue tunnel, and I do that with ingress replication. So I have a full abstraction. So if you would use ingress replication in site 1, the TOR you're seeing here in site 1 would send it to every TOR within site 1, but not to site N. Border gateway 1 would take it and would send one ingress replication copy to site N, and then the border gateways there will replicate it again. So you get efficiency of what we call DCI layers. Maybe you only have 1 gig or 10 gig and not the wide 40 or 100 gigs you might have within your data center. So we optimize that piece for you, which gives me everything is now multiple. So we brought back the hierarchies into the overlays and isolated the underlays as a result of this. Yes, I think I'm done. I think we talked about all of this. I hope you guys are happy. 2 references, 2035, as said, tomorrow morning, 8:30. The other one in the afternoon, we're talking about VXLAN OEM. So like how you do operation and visibility in there. If you still don't have enough, you can get some more insomnia by reading what we wrote. If you want a signature for that, we are having a book signing tomorrow between 1 and 2. Some links, and thank you very much for coming in. Ask questions after it, and please complete the survey if you can. I wish you a great rest of your day. Thank you very much.